Hello everybody, welcome to Unit 8 Part 2 where we are going to start graphing the functions and working with those graphs. So let's dive right in. The first thing you need to think about before we're going to deal with any sort of graphing is starting to shift your understanding to the sine as a function. So the first thing I want to look at is this chart. Thinking about what the sine values are, and notice that the angles are all in radians. So if it helps you, and this is perfectly appropriate, start identifying where some of the major angles are, 270 and then back to 360. And you can do that in degrees, but I really do want to push you guys to start thinking in radians. It can be really helpful if you just see pi over 6 and immediately imagine that 30 degrees without even having to do that conversion or that translation in your head. Either way, let's jump right in and start filling out this table. The sine is the height on the unit circle. It's the y value of the angle, of the point that the angle makes, rather. The sine of the angle is the y coordinate. It is the height of the point on the unit circle. So when we start rotating, that height is at 0. It climbs to a maximum of 1. It falls back down to 0. It drops in those negative quadrants down to -1, and then it climbs back up to 0. In between, we can get those exact values. At pi over 6, think of your little unit circle. Pi over 6 is the lower angle. The height right there is then therefore my 0.5. Then I hit root 2 over 2, which is approximately 0.707 or 0.71. And then at the taller angle, that height right there is root 3 over 2, which is approximately 0.866, so we can round that to 0.87 for our purposes. Now I'm going to start using kind of that mirror. Now it's going to start falling. Go 0.87 to 0.71 to 0.5, back down to 0. Now I'm going to drop into the negatives. Now I'm going to climb back up to 0. If we consider this chart to be a function, which means that we take an x and we input it into a function to get out a y value. F of x is a y value. Plug in x, get out y. That's how we get coordinate points. Plug in x, get out a y. These are our x values and these are our y values. We therefore have a graph that we can graph. Let's move on to that. Here's that same table again, and now I have some axes down below. Notice that my x-axis is labeled in terms of radians, 0 through 2 pi. I can identify that my maximum and minimum values are 1 and -1, so I can go ahead and make this a 1 and this a -1, which leaves me with 0.5 and -0.5 halfway across, and I can just start graphing. I'm going to do this in red so that I can be consistent across the rest of the lesson. This is an XY point. Plug in 0, get out 0. Plug in pi over 2, get out a 1. Plug in pi, get out a 0. Plug in 3 pi over 2, out -1, and then back up to 0. Now you can visually see what I was saying earlier, where the value literally rises, comes back down to 0, drops to negative, and comes back up again. I do these points first because these are those major axes that are really easy to graph. They're easy to picture. These are a little bit trickier. And so I like to kind of have this framework here first that I'm going to fill these in between. The next easiest number to graph is the 0.5s, just because it's a nice round decimal. we have to identify where pi over 6 is on this axis. Remember that what we're doing in that quadrant on the unit circle is we're dividing it into 3, and this is pi over 6, pi over 3, and pi over 2. Well, here's pi over 2 divided into 3. So my increments on this graph are pi over 6 increments. Notice that that means that this is pi over 6 and this is pi over 3. Pi over 4 isn't on an increment. We have to find that separately. But I can go ahead and graph my pi over 6. I'm going to skip the pi over 3 for now. I'm going to go straight for my 0.5s because they're so easy to graph. Now I'm going to come back and I'm going to do those pi over 6s. Or sorry, the pi over 3s. 0.87. Let's see. This is 0.5. That makes this 0.75. So we have to go a little bit higher yet. Approximately there. And now notice I'm not even looking at whatever angle this is. I'm just using the reflection, and I know that that's where the next point is going to go. Same thing over here and here to the left and right of 3 pi over 2. Without even having to conceptualize what that angle is, I know that I'm going to be right here and right here. And I realize as soon as I do that, that I've made an error in these 2 points. So let's go back and fix that really quickly, because I did not graph those at 0.5 correctly. There's my 0.5. Now you can see the smooth curve. Let's go back, and lastly, let's fill in the pi over 4. Pi over 4 is taking the pi over 2 and 0 and splitting it in half. So I'm literally going right in half in the middle of each quadrant. So there's my pi over 4. And I'm going to graph 0.71. Remember that this is 0.75, so I'm going to be just below that. And I'm going to be just below that on each side. And in this case, I'm going to be right above it because I'm going to be less negative. There's our graph. All that's left for us now is to fill it in. Really nice and smooth. And there we go. That's your sine waves, ladies and gentlemen. Sine wave. Okay, let's watch a short video to help you conceptualize a little bit further. 3 minutes for this video only, okay? Let me see, I need to go here.
Today's video, we'll learn about sine waves, light, sound, a mechanical spring, and even electricity coming to your house behave like a sine wave. But did you ever wonder why the sine curve is shaped this way? And what does the word sine even mean? Well, you'll find out in today's video. To begin, let's consider the Hong Kong observation wheel to understand a sine wave, or the London Eye, or any other Ferris or giant wheel. They're all circular. Let's assume it rotates counterclockwise, and you're taking a ride on it. There you are, as a red square, and it takes about 20 minutes to complete one rotation. Well, if you track the motion, you'll just go around in a circle and end up at the starting position in 20 minutes. But what if, instead of looking at the giant wheel from the front, we look at it from the side? So rotating the giant wheel towards us until it ends up looking like this. As you look at it from the side, it just looks like a vertical line. Here are the two views, A and B. Now, as the giant wheel rotates, the movement of the red square in view A is just in a straight vertical line, going up and down, and in view B, just in a simple circular motion. So we just took a two-dimensional motion on the right in view B with both vertical and horizontal components shown in blue and turned it into a one-dimensional motion, just vertical, as seen on the left in view A. So we start at time 0. In 5 minutes, you reach the top of the giant wheel. In 10, you're halfway around. In 15, you're at the bottom. And in 20, back to your start or original position. On a position versus time graph with the minutes marked, First, if the giant wheel is not rotating, no matter how much time passes, the red square will stay at the same position. Notice as time passes, position stays the same. So all you get is a horizontal line, again showing no movement. Now let's plot the red square's movement when the giant wheel starts rotating on our time versus position graph for this vertical motion. From the start position, in 5 minutes, you'll reach the top of the giant wheel. In 10 minutes, you're back down to the start position. In 15, you're at the bottom of the giant wheel. Finally, in 20 minutes, you're back again at the start position. So here we go. This red curve is a sine wave. Again, notice the movement of the red square is just up and down vertically. When plotting this vertical movement on a time axis, that's where the sine wave gets its shape. So a sine wave waves, or using a fancier word, oscillates back and forth from the start position to a maximum amount in either direction, which is called its amplitude. It's merely one of the components of a simple circular motion, so no wonder it repeats over and over, like a giant wheel ride. Another key concept.
Okay, we don't need to worry about that other key concept. That's okay. You can go to the link though and look more if you want to. Okay, here's an interactive graph that can help you. I will post all of these links for you. On this interactive graph, I encourage you to use the slider to start at the starting position and slowly increase the angle to see how the unit circle connects to the graph of the function. You can play with this a little bit and you can see what happens. Notice what's going on over here. This is a question I have for you. What happens after you rotate all the way around to 2 pi? That graph kept going. Because if you think about it in terms of the wheel, as he was saying, let's call this 1. I don't need to graph it more higher than that. Call that a 1. I'm going to return to 0. The wheel's going to keep going around. Every 5 minutes on his graph, or pi over 2 on ours, we're going to reach again the height, back down to the middle, back down to the bottom, back up. And that would work working backwards too. You could think about it in terms of the unit circle and rotating backwards. If I rotate backwards, I'm going to go down. Did I go too far? I did. There we go, down. And then back up as I rotate all the way around to negative pi, back up to 0. Rotate to negative 3 pi over 2. Now I'm at my height. The pattern keeps going in both directions. And I can use this to fill in a much more complete sine wave. I don't have those middle of the quadrant points in here, so it's a little bit sloppier. But you can see really how the function goes forever in both directions. A little bit less pointy than I have right there, but you get the general shape.